Okay, we're going live, and I'm live. I'm just double checking. Here, seems like we're on. Going live. All right, let's do it. So we're taking a look at, I'm taking a look at Newton's laws versus Lagrangian mechanics. They're both of them are kind of 6 of one, half dozen the other. Like you can, but sometimes with Newton's laws, things get really cumbersome because you have to identify all the forces and all the accelerations in order to figure out like what is my equation of motion and like how is this thing moving. And sometimes it gets confusing of like, is this a constraint force? Is this an applied force? Meanwhile, Lagrangian, if I know my degrees of freedom, kind of do an initial check of like what's moving, how is it moving, then we can jump straight into like how do I define kinetic and potential energy. So here, this is like what is my KE, that's my T, what is my potential energy, that's my V. Are there any external forces? Like, is there anything like are there external forces? External or non-conservative? Oh. Trying to get rid of those. That's part of it. Versus here, we've got give me back my pointer. It wants to write, but it just is having trouble. There we go. Where here we have our sum of the forces is ma. So we need to know what are all those forces in order to figure out. Meanwhile, kinetic energy is always some function of speed. How fast am I moving? Not even where. So kinetic energy doesn't really care where we're going. It's just measuring how fast we're going. And then this is always some function of position. Very different than over here where forces, total force is a function of both position and velocity. Not always velocity, sometimes it's speed, but somehow position velocity, and that's equal to mass times acceleration. All right, so best way to try this out is let's look at kind of a familiar example. If I have a mass connected to a spring, then my classic Newton's method is that I have kx acting in this direction. My acceleration is in the opposite direction, at least if I'm going to say like this is here's my x, here's my y. So now, let's get rid of that. And, so many dots here. Negative kx equals mx double dot. So x double dot, my equation of motion is now, x double dot is a negative k over m times x. And there, it's pretty straightforward, not a lot going on. Versus here in my Lagrange approach, I say, what is my kinetic energy? Well, it's going to be 1/2 mv squared, which I'm describing everything in terms of x over here. So let's describe it there too. So 1/2 mx dot squared. And as here's a little note, d dt of, let's say, f of any function is the same thing as writing f dot. And then d squared dt squared f double dot. Okay, and now my potential energy, V, is going to be a 1/2 k delta x squared. I'm just going to write x, just saying that if x is 0, then we have no spring stretching, so let's just call it that, kx squared. And one way of looking at this is like with conservation of energy, 1/2 m x dot squared plus 1/2 k x squared is a constant. It does not tell us, this does not, like, it's not the same thing. It's not an equation of motion. It definitely gives us a relation between speed and position, but we need to know, I mean, technically, even with this equation of motion, we would need to know something about its initial position and its initial velocity, and then we could solve for other parts, but it's not an equation of motion. So it is not an equation of motion. The Lagrangian part is that here, if I say ddt of dt, I'm going to write out the yeah, let's do this, of, and should I write out, let's write the L minus dl dx equals all the other forces out here, and really it's the generalized forces. So this would be stuff like if I was applying a force, like if I had some kind of force here, what is the component F dotted with that delta X? And that would be like what are the work conjugate kind of things in there. So in this case, I don't have any external or non-conservative forces, so this whole thing is going to be 0. Like, well, what is this L term? Like, where did that come from? So let's write that out. L is T minus V. This is called the Lagrangian, named after Lagrange, or action. Lagrange called it the action. Like, this is how much action something has. It's kinetic minus its potential energy. And the whole idea of Lagrange mechanics is that if a system is moving, it's going to take the path of least action. Little different from like least energy path, but the very similar. Since we're still dealing with kinetic and potential energy, it's very similar to that same, like, Hamilton was the one who said T plus V is a total, that's a constant, and we're going to take the path of least energy or least resistance, but this line of least action, or the motion of least action, that's where we're going to get our equation of motion there. So T minus V, so that's 1/2 m x dot squared minus 1/2 m x squared. That's our L. So dl dx dot is mx dot. dl dx is m. Oh, why did I write m? I'm losing control of my pen. So dl dx is, let's let's see if I can delete this. K, there we go, is kx, like that. So I think you see where this is all kind of going. So d dt of mx dot equals that negative dl dx. So a negative, and here really this is like negative negative, so we end up with a equals negative kx. So mx double dot is a negative kx. Now, for sure, we did more steps to get from here to here than here to there. But we're only dealing with one single force, 1 degree of freedom, 1 force acting on our item. And in both cases, we still end up with same equation of motion. Negative k over m times that x. So it's more work to start, but the nice part is we started with a Lagrangian, which is a scalar item. So because it's scalar, in this case we ended up dealing with only scalar values because the vectors were all aligned with each other. In this case we were dealing with scalar items because that was how we're actually dealing with things. And let's make new page. Because what if we have a pendulum that can also roll, like it can move around, and maybe we even know like it can roll, and we're going to say that this has some like y of t, like I know what that function is, or I can prescribe, maybe that function is something that I want to change. So theta here, so in the Newtonian frame I would need to say, all right, I've got mg, I have this tension, but that tension is a function of that y of t. Like as I'm moving this thing around, it's not a fixed coordinate system. Like I've got this has some like y of t method to it. So whenever I look at like my acceleration, I need to consider both my radial acceleration, my tangential acceleration, and I need to consider this acceleration of left and right motion. So if it's a constant speed, then maybe that's a 0. If it's not, maybe it's not. But already just in this case, we still have kind of a 1 degree of freedom problem. Like we have 2 things moving, both the base and the object, but only the object is free to move. The base, we're going to say, is some fixed motion. So it gets pretty complicated right off the bat because y is not in line with either ma theta or mar. We can make some small angle approximations to kind of say like this y double dot is a theta, like it's in line with it. It's not the same, but we can add it in there. But it gets a little tricky pretty quickly. But so that's our kind of Newtonian start. Is we have a free body diagram and we have our kinetic diagram, which is now 2 parts of a frame, a moving frame, and the reference frame that is moving, how it's moving. All right, let's consider the Lagrangian instead. All right, what is kinetic energy? Well, it's still 1/2 mv squared. It didn't change. We're still calling it 1/2 mv squared. The difference here is that my equation, I want to turn it into some kind of theta. Like, so if y is 0, then, so if, let's say y of t is constant. It's some value, but then theta double dot is a negative g over L times sine of theta. And that's something I can go through and kind of solve that. But it's a limiting case, just when y of t is constant, or it's or y dot of t is constant. Like, as long as y double dot is 0. So there's that. So I want to get this in terms of theta, and then I can also use this y of t. So let's look at our reference and say this is my y dot. This is my theta. So my x position, if I want to say, like, where is this thing, I'll call it x. All this is like our current y position. Call it xp, and maybe yp, like this. xp along the I plus yp along the j. So xp is going to be L times that sine theta. And that's along my I, at least in this chosen kind of 90-degree rotation. And then my y position is this, it's L sine, oh, whoops, that should be L cosine, right? That's why I shifted it. So L cosine is my x, which makes more sense. And now I have that L sine theta along the j, but I also have that y position, so plus y along that j. Cool. Now velocity is going to be L theta dot times, and that'll be a negative, but we don't, it's okay, we'll add it. And then plus L theta dot cosine theta plus y dot all along that j direction. So when I talk about v squared, really I'm talking about the dot product of, like, what is v dot v? V dotted with v, which is 1/2 m times L theta dot L squared theta dot squared sine squared. So I'll just write s squared theta plus this squared term of this j component, L theta dot. I'm going to write c theta plus y dot squared. Now I can kind of separate out those terms. So I'll have a L squared theta dot squared cosine squared, so that's going to be just one term here. So the sine squared plus cosine theta squared adds up to 1, and then I should have a y dot squared here. But then there's also one more kind of linking factor between the two. So L y dot theta dot times that cosine theta. So our kinetic energy, we used some vectors to kind of get it, but at the end of the day, why is it doing that? I don't mean to delete that. I'm just going to leave it. Nope. It keeps deleting what I'm trying to do. Okay. We'll leave it. Oh no. There we go. Cool. And now V is mgh. I don't have any springs. And H is really mg of R dotted with our x, with our I direction. It's one way, like if we're at x equals 0, we could say that that's 0 mgh, or that h is 0. We could try to subtract it and get to like, all right, if theta is 0, that's our minimum potential energy. But this is a quick way to just jump right into it. I'm just saying like, well, what is my I component of my position? So it's mgl times, and I guess really it's a negative, right? mgl, that negative mgl cosine theta. Is it negative? Yep. Because distance here, like the gravity is acting down. So the more we go up along the x-axis, the more potential energy we have as we kind of come back down. All right, cool. So we're making some progress. We can say L is that T minus V, or 1/2 m L squared theta dot squared plus y dot squared plus Ly dot theta dot cosine theta minus, so we'll say plus mg L cosine theta. And I think I'm doing that. Sometimes I mess up the signs here and there, but we'll give it a shot. I think I'm on the right track. We'll find out in a second, right? And it's always the same kind of form. ddt of dl d, in this case it's a theta dot, minus a dl d theta equals a 0. And this is different than the Newtonian part, because in Newton mechanics we need to know what are all those forces, like where are all these forces going. But here there's got to be a force creating y of t, but it's a constraint on motion. So if it's a constraint on motion, I don't need to know what forces are actually causing that, because I'm saying this is the motion that has to happen. So all I care about is just how do I define kinetic and potential energies. All right, so where do we have theta dots? Only in the kinetic energy, and we only have theta, and theta does come up in both kinetic and potential here and here. So let's see this. dl d theta dot is m L squared theta dot, and the y dot goes to 0, the plus L y dot cosine theta, and then that's it. That's our dot there. So dl d theta, which is going to be those other terms, is going to be my, oh, you know what? Still need that 1/2 m, right? 1/2 m L y dot cosine theta, like that. All right, so now when I take a derivative I'll have a 1/2 m L y dot and a theta dot times the sine of theta. And is that a negative sign? Derivative of cosine becomes a negative sign. And then a minus mgl sine of theta. So now I need another derivative of that dl d theta dot. So I end up with ml squared theta double dot plus a 1/2 ml y double dot times cosine of theta, and then minus a 1/2 ml y dot theta dot sine of theta, taking derivatives of those two terms there. And now I'll subtract from that dl dt, so a minus plus a 1/2 ml y dot theta dot sine theta. Those two cancel out. And then a plus an mgl sine theta. So now let's get this all, and this whole thing is all equal to 0. So let's divide through by that ml squared and kind of get things all lined up. So theta double dot is a negative g over L times that sine of theta minus ml squared, so that would be a y double dot over L over 2L. Pretty sure there's a 2L in there. Times that cosine theta, like this. And did I do all that right? Trying to get that ml squared over there. I think we're good, yeah. And sure enough, just like I had said in the beginning, like if y double dot is 0, then we end up exactly where we started with Newtonian mechanics. But now we have this extra term of like if we're moving this thing back and forth, or if we're accelerating it, like if this thing is just moving, if we're accelerating the base of our pendulum, like putting a grandfather clock on a moving truck and we hit the brakes, what's going to happen to that natural frequency, or how is the swinging going to change? All of that is kind of contained right in here, just like that. Cool. So that's what I wanted to show for today, at least getting started here, was just a comparison between, like, yes, there's definitely different work involved. You need to define kinetic and potential, and you have to be careful about how you are defining those. But the benefit is that you can start looking at more types of motion and more constraints on motion. And then we'll get into the details about like why does this equation work? It's like, well, I kind of pulled it out and just said like this is a Lagrange equation, but we'll get there. So we'll figure out how to get this to work and work on getting more understanding about like where these Lagrange equations come from, how they work, and all of that. All right, that's all I had for today, and I will see you next time.